only thing, yeah, now it is okay.
Yeah, you have already covered, I think, up to complemented lattices. Is that right? Hello?
Yes, yes,
Yeah.
yes.
So let us start with Boolean lattices. So Boolean lattices are bounded distributive complemented lattices, or you can put them in any order. Boolean complemented distributive lattice. So they satisfy all the properties. So very well behaved lattices actually. So now this Boolean lattices, they have, so because they are bounded, they'll have extreme elements. So the max may be called as zero, as one, and the mean may be called as zero. Of course, because these are distributive lattices, this this distributivity gives rise to interesting properties. That is, each element has a unique complement, because you have studied that in a bounded complemented lattice, bounded complemented distributive lattice, every element has a unique complement. Okay, and De Morgan's laws also apply. So, these are the statements of De Morgan's laws. That is, the complement of the meat, the complement of the meat is the join of the complements, and the complement of the join is the meat of the complements. All right. So, how can we prove this? So we basically prove that you have two expressions here. You have you have two expressions here. Sorry, just you have two expressions here, and you have got another expression here. And you got to show that this expression is the complement of this expression. So they have to satisfy the properties of complement. That means their meat should be 0 and their join should be 1. So we just need to verify these two properties. So, so here is the property that their meat is 0. So here what you see is that we are just making use of the distributive property. So as you can see, this is distributing into this. All right, this is distributing into this, and after that, it is quite easy to see that um, the property is satisfied. All right. So these are 0 actually. So so these are the properties that we are using. So you have shown that we have been able to show that the meat of complements is uh, you know meet of these complements, or the expressions that you are claiming to be complements, those are 0, and their join should be 1. So once again we carry out a similar exercise, and then you see that you can follow the steps. These are straightforward steps. So you find that the join of those two expressions is 1. So you can say that those are complements. So the other property can also be shown. So that's how you can show that De Morgan's laws apply in a Boolean lattice. Okay. Now uh, let us try to understand the structure of a Boolean lattice. So let us consider a lattice with a minimum element. Let's say that is 0. Now we consider what is meant by an element being joined irreducible. Just a minute. Uh, so when we say that an element is joined irreducible, what we simply mean is that you cannot express that element as the join of two other elements. Okay. That is what is meant by, or what should I say, you cannot express an element as a non-trivial join of two elements. Alright. So what is a non-trivial join? So let us look at this picture. Okay. So let us look at this picture. So here you have two elements, B1 and B2, where we have B1 not equal to B2 and not even, and then you have this element A here. You have this element A, which is the join of B1 and B2. So you can see that this is a non-trivial join because we are getting this element A by joining two distinct elements, B1 and B2. Okay, so you are basically here A is the join of B1. It is the join of B1 and B2. So this is a non-trivial join. Okay, this is a non-trivial join. Now, in this case, you could express A as the join of A and C, but this is, you can say it's kind of trivial because this will always be satisfied. This will always be satisfied. So this is a situation, when you have a situation like this, that means when an element has a unique predecessor. In this case, the element doesn't have a unique predecessor. It has got two distinct, you can have two or more, but you have got two distinct predecessors. So in this case, you can non-trivially express A as the join of B1 and B2, but in this case, you cannot non-trivially express A as the join of two distinct elements. Alright. So A is, in this case, A is join irreducible. Okay. You cannot express A as the join of two distinct elements. So that is, basically what this definition is. This definition essentially captures that notion. So an element A is join irreducible if A cannot be expressed as the join of two elements, two distinct elements, X and Y, or doesn't have to be two distinct elements. You cannot even express it. For example, you can't even express it as you can't even write it like this. Even this is not possible. So you can't. So in other words, it has to be. I mean, if you express it as the join of x and y, then one of these elements must be this element itself. This is trivial. This is trivial. All right. So in other words, if you express, so if A is join irreducible, then if you express A as the join, as a join expression, then one of the elements has to be A. You cannot have it otherwise. So that is an example. So that is what is meant by join irreducible. Now 0 is always join irreducible. The minimum element of a lattice is always join irreducible. All right. So what we have here, what we have here is, if B1 and B2 are immediate predecessors of C, all right, if these are immediate predecessors of C, then you can write immediate, actually you can say distinct predecessors of C. Then you can write C as the join of B1 and B2. Now, an element A, which is not the minimum element, not 0, it is join irreducible. It is join irreducible if and only if it has a unique immediate predecessor. So that is just what I discussed. And elements immediately succeeding 0 are atoms, and those are join irreducible. So in this, this in fact is a lattice. This particular, and here in this case B1 and B2, these are atoms. All right, these are atoms. Both B1 and B2 are atoms. So these are these are immediately succeeding 0, and these are also join irreducible, as you can see. So any element can be expressed as a join of a set of atoms. Any element can be expressed as a join of a set of atoms. So of course, if you have n atoms, then you would expect, so how many possible subsets can you have? You can have 2 to the power n possible subsets of n atoms. So you would expect, I mean, you would expect a lattice to have 2 to the power n elements, if each element can be expressed as the join of a set of atoms. Okay. Now, in case of a diamond lattice, so you probably remember the structure of a diamond lattice. This is the structure of a diamond lattice. So you can see that this element 1, this element 0. So you can see that 1 can be, so these are all atoms, by the way. These are all atoms. So A can be expressed as, in many ways in fact, as you can see, it can be expressed as uh, so what it means is that it is not unique. It is not unique. So in a distributive lattice, in a diamond lattice, so diamond lattice is not distributive, by the way. So so in a non-distributive lattice, that representation is not unique. Now, so what you're saying is that for a finite lattice, we can express A as the join of joint irreducible elements. Okay, you can express A as the join of joint irreducible elements. And so any joint irreducible element will be, expressible in this. I mean, if you have a joint irreducible element, and if it is expressed as the join of two joint irreducible elements, then one of the elements, must be the same. For example, because these are joint irreducible, so dj, if dj is expressed as the join of two joint irreducible elements, then one of those must be dj. And then you will also have the situation that di will be a predecessor of dj. All right. So if you have such a situation, then you can do away with di. You don't really need to have di in that. You can drop di. So if you reduce this expression in that manner, then you can make this expression e-redundant, so that you do not have any such any di which is a predecessor of dj in that list. Okay, so that makes the representation e-redundant. Means you can't. So if you put an element which is a predecessor of one of these, then that becomes redundant. Okay. So then such an expression is unique up to permutation, because join is commutative. So any permutation of that of these elements will will have the same value, will be the same. So it is unique only up to permutation for a distributive lattice. So let us just look at that. Let us just see why we have a redundant irreducible sum. So suppose that the representation is not unique. So in other words, let us say that we can express an element A in these two ways. Okay, we have two ways of expressing an element as the irredundant irreducible sum representation. So here we assume that each of these elements C1, C2, Cm or D1, D2, Dn, these are all irreducible. These are all joint irreducible elements. All right. So what you can see is that for any Ci or Dj, any Ci or Dj will satisfy this property. Will be a predecessor of this. All right. Any Ci or Dj. So we can therefore write it in this form. We can. I mean, this is a simple, property of the meat. So you can write Ci in this form. And then you can apply distributivity because we have assumed that distributivity holds in this lattice. Now, since Ci is joint irreducible, so because this Ci is joint irreducible, so if we go by the property of joint irreducibility, so one of these elements must be equal to Ci, must be the same as Ci, because Ci is joint irreducible. So there must exist a Dj, so that this one of these elements is same as Ci. Okay, so if you have this property, if it works out this way, then Ci must be a predecessor of Dj. And if you carry out a similar exercise with Dj, then you will have a similar situation that there must be a Ck, so that Dj is a predecessor of Ck. So you have this this situation that Ci is a predecessor of Dj is a predecessor of Ck. But you have assumed that the sum is redundant. That means, see, if Ci, by transitivity, Ci is a predecessor of Ck, but you have assumed that this sum is irredundant. So if this situation exists, then Ci has to be equal to Ck, and that makes Dj equal to Ci. Okay, that makes Dj equal to Ci. So Ci and Dj must be identical. So you can basically replace. You can replace Ci with Dj or Dj with Ci, either way. I mean, they are identical. So you just that those are identical. So this way, if you carry on, you can pair off all the Ci's with all the Dj's, and that way you can show that the sum representation, if you have an irredundant, this irredundant irreducible sum representation is unique up to permutation, of course. Okay, this will be unique up to permutation. So that is an important property of an important property. That means so you know that so if you consider the atoms, you can have 2 to the power n possible subsets. The atoms are all irredundant, and any subset will represent an irredundant irreducible sum. So that is a a strong suggestion that that could be the number of elements in a Boolean lattice, which is a bounded, complemented, and distributive lattice. But the question is, can you have, what we are saying is that you have, I mean, so you have, these are your, this is 0. So these are your atoms, all right. And what we have said is that, what we have seen rather, is that uh, oh, anyway, this is not a big deal, but what you have seen is that you can if these are your atoms, this is A1, A2. So all these atoms are irreducible, okay? All these atoms are irreducible. But can you have, question is, so you have a 1 somewhere out here, right? You have a 1 somewhere out here. You have a 1 somewhere out there, so. So question is, can you have, is this possible? Is this possible? Can you have, so in this case, if you have such a thing, then this will be join irreducible, right? This one will be join irreducible. But is this possible? Is this possible in a Boolean lattice? So what is a Boolean lattice? It is complemented, rather let us say that first of all it is bounded. It is bounded, it is complemented, and it has this maximum element. I'm forgetting that term, just a minute. Yeah, it is bounded, of course, it is bounded, complemented, distributive. Bounded, complemented, and distributive. Okay. Uh, so can we have uh, can you have irreducible elements somewhere in between? So note that in this situation you have unique complements. You have unique complements. So let us see what happens. Let us see what happens with respect to complement. So here you have an element Z, you have an element A, and you have an element Z. Okay, you have an element Z, which is its complement. Okay, which is the complement of A. So if it is the complement of A, then these two properties are going to be satisfied. As you know, if Z is the complement of A, then these two properties are going to be satisfied. Now suppose A has B as the unique predecessor. Okay, suppose A has B as the unique predecessor. Alright. And we consider that B is not 0. So what you see is that, so now just see the join of B and Z. The join of B and Z will be same as the join of A and Z, from the structure. The join of B and Z will be somewhere over here. Let us say the join of, so obviously the join of B and Z will also be the join of A and Z, and similarly, so this is 1. Because the join of A and Z is 1, and similarly you have 0 somewhere over here. So by the same argument, the meet of B and Z will be same as the meet of A and Z, which is 0. Alright. So what you find is that B is also a complement of Z. So now Z doesn't have a unique complement. All right, if you have such a situation where B is not 0, then an element like Z, which is the complement of A, will also have to be the complement of B. So therefore Z doesn't have a unique complement. So what you can see is that in a Boolean lattice, such a situation is not possible, because as you have seen, every element in a Boolean lattice has a unique complement. So in a Boolean lattice, what you can see is that the only irreducible elements, the only non-trivial joint irreducible elements are the atoms. These are the only atoms, and these are the only non-trivial or non-zero joint irreducible elements. You can't have any other joint irreducible elements in a Boolean lattice. Okay, so that's a very interesting property. So now, as you can see, I mean, what we have already seen is that you would expect a Boolean lattice to have exactly 2 to the power n elements, where n is the number of atoms in a Boolean lattice. All right. So, in fact, that leads us to a particular representation of a Boolean lattice, which is called the stone representation. All right. So, as you have seen, that because of this, the property that we saw some time back, that any element can be expressed as an irredundant, irreducible sum of the atoms. In case of a Boolean lattice, those will be the atoms. So that, also suggests that, there is an isomorphism between Boolean lattices and power sets, because after all, how many possible what are the possible irredundant sums of the atoms? Those are the those are the various subsets of the atoms, because it's unique only up to permutation. So any subset of these atoms will or you can say the join of any subset of the atoms of a Boolean lattice will be an irredundant, irreducible joint representation of an element. So basically every element corresponds to a subset of the atoms of a Boolean lattice. So in other words, you would expect an isomorphism between the power set of an element, the power sets of a set of n elements to the Boolean lattice constructed from n atoms. As you have already seen, the power sets of given set of elements, those form a lattice. In fact, those you will see that those actually form a Boolean lattice. So let us just see how you can come to that as well. How you can come to that representation. So at the bottom you have 0, and then the atoms, in this case ABC, those are present directly above the level 0. So let's say that 0 is at level 0. All the atoms are present at level 1 as shown over there. And those are akin to the singleton sets A1, A2, AN, and so on. or in this case, yeah, just a minute, please. I'll- yeah, okay. So, all right. Yeah. So the structure we are building the structure bottom up. So this is as I said, this is level 0, this is level 1. All right. So and then we have over here level 2, and finally you have level 3. So in level 0 you have subsets with 0 elements. In level 1 you have subsets with 1 element. In level 2 you have subsets with 2 elements. And here you have level 3, which is really your subsets with all the 3 elements. Alright, that is 1, which is which is 1. Alright. So what you do is, to go to the next level, you join pairs of elements y1 and y2 at level I, such that at level I, uh, such that you know so there is a set difference. So if you take the set difference, they differ by 1 element. So the result is that the resulting element is the elements which have. So when we say this, so what is yi? So yi, let us say, what is yi? Yi is uh, you know sorry, yi. Uh, yi is the set of elements. So yi at, or rather we can say y k yj at level I. Okay, you are saying that yj at level I. So At level I means you are going to have elements A, I1, A, I2, A, I, level I. So you have got so many Li, you have got Li distinct elements. And it is really, so the particular element, yi, you can say the particular element, say, this particular element y is simply the join of all these elements. It's simply the join of all these elements. So this subset represents a particular element as the join of these. These are the atoms. These are the atoms of the Boolean lattice. So as you can see, this is how. So when you say that y is the union, so we just take the union of all these atoms of this set of atoms, and this is the new element which is formed at the next level. Okay, this is the element which is formed at the next level. So this is how it goes on. This is how you, if you think in terms of constructing elements or representing elements as the irreducible, redundant sum of the atoms, that is how you can build the Boolean lattice. If you want to think of the meat, well, you can come down. I mean, the meat will also work out in the same way. It will also work out in the same way. But it is enough to consider the join. It is enough to consider the join. I mean, this is enough. This is just, for your information. This will also happen, but this is enough to consider the joint. So, as you can see, there will be a combination of I elements taken n at a time in each level, and you'll have a total of 2 to the power n elements. So this is the the stone representation of a Boolean lattice, and as you can see, there is also you can see how this is related to the power set lattice. And you have already seen that a power set lattice is a Boolean lattice. In fact, a power set lattice is also a Boolean lattice. Okay, and in case of a power set lattice, the only difference is that instead of this, so if you consider these as sets. If you consider these as sets, the power set lattice, what you find is that this is just replaced by the union of so if you consider these as sets, this is just the union of these sets. And this is the union of, you take any pair, it turns out to be the same. So this is really, you can say, so A union B is of course AB union, say, AC is equal to AB union BC is equal to AC union BC. All right. So, as you can see, you get the correspondence between Boolean parts set lattice and Boolean algebra constructed out of the atoms A, B, and C. All right. So now let us come to Boolean algebra. So we have studied basically a lattice is a structure. The lattice is a structure, as you have seen. So let us now see how it relates to Boolean algebra. So you have already seen what a Boolean lattice is like, and we consider the algebraic system which over the set A. So the set A is the same. Set A is the set of atoms. So we are considering Boolean algebra, and what we are doing is the join operation is mapped to plus. The meet operation is mapped to dot. This plus is often called OR. The dot is often called AND. And this is for all elements in A. And the complement of any element, because this is an algebraic system with plus, dot, and complement. So the complement of an element X is an element Z satisfying the complementation laws in a lattice. Okay. So the complement of X is an element Z satisfying the complementation properties. And as we know, as you have already seen, that in a Boolean lattice the complements are unique. So in a Boolean algebra also we'd expect the complements to be unique. And so Huntington's postulates, this was proposed independently. This Huntington's postulates, these were proposed independently. So these are some of the laws of the postulates, and we find that when you consider mapping of a Boolean lattice to a Boolean algebra as defined by the Huntington's postulates, then you find that this commutativity, distributive laws, identity laws, complementation laws, these are the same as the laws of as the properties that are satisfied in a Boolean lattice. So these laws are consistent with the properties of a Boolean lattice. Okay. These are the laws of Huntington's postulates for a Boolean algebra. And what you find is that you have already studied the properties of a Boolean lattice. So essentially we are mapping. So you can say that. So this is the commutativity law. You have already seen that this is satisfied in a Boolean lattice, for example. So everywhere you can just consider the corresponding. I mean, this is just, you can say, like renaming the operations. So x dot y is really the join of x and y, which you have seen is the join of y and x. So these postulates, these laws of Boolean algebra as presented in the Huntington's as presented in Huntington's postulates are 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 consistent with the properties of elements in a Boolean lattice. Now, you have other properties which may be proven using this laws of Huntington of Huntington's postulates, or using the Huntington's postulates. So here is a proof of these properties. So idempotence x or x. So as you can see, you can write it in this form, and well, these are some steps which you can. These are some steps, because you can always write it in this form, and for any element x or x is 1, and then you can distribute. You're applying distributivity. So this way you are able to prove that x or x is x. So these are certain proofs that you can achieve through this Huntington's postulate. So these are various proofs. Here you can prove idempotence, you can prove absorption. So some of these proofs are given here. This is boundedness and annihilation. So you have similar properties in a lattice. You have the same properties in a lattice, but these properties can also be proven. These properties can also be proven using Huntington's postulates. Now you can define. You can define this and, or, and not operations through these truth tables, as shown, as indicated. So then you have this associativity properties, which can also be proven using this Huntington's postulate. See, these are some steps which you can just follow and to establish the proofs. So you can just go through these yourself. So we essentially want to prove that these two expressions are identical. That is what we are achieving finally. That is what we are achieving finally. So we achieved this through some intermediate expressions. We derive, show that ax is a, bx is b, cx is c, and then we show that yx is same as y, and xy is same as x. All right. So that way you can show that because xy is same as x, and these two are also same by commutativity. So you show that x is equal to xy. So x is equal to xy. X is equal to xy, and that is equal to yx, and that is equal to y. So that is essentially what is being established. And in between, you make use of these properties. All right. So this gives you an axiomatic proof of the associativity of Boolean, uh, Boolean, you can say OR. So these are uh, various properties which you can also prove axiomatically. So these are, I mean, the point to note is that these are axiomatic proofs as against the proofs that we had given earlier. Those are structural proofs. Those are based on the structure of the lattice. And these are based on, these axioms of Huntington's, or you can say the Huntington's postulates. So those Huntington's postulates are essentially axioms. Okay, so essentially, what you have seen is that, uh, I mean, if you go by these proofs, essentially what you find is that um, uh, the properties of Boolean algebra are consistent with those of a Boolean lattice. So it shows that all the properties that you can derive for uh, Boolean algebras using Huntington's postulates, those are essentially are the same properties that you had for a Boolean lattice. So you are able to show that a Boolean lattice is a Boolean algebra, also a Boolean algebra is a Boolean lattice. All right. So this basically just relates your Boolean lattices to Boolean algebras. All right. So let us now take a look at Boolean algebras. Okay, so let us consider three sets A, B, and C. Okay, and what you see here are all possible, intersections of these sets, and we are just labeling those as various regions. So we are we are labeling this region as 1, this region as 2, this region as 3, this region as 4, this one as 5, this one as 6, and this one as 7. Okay, we are referring to these regions. We are marking off. We are marking various regions. So what you can see is that any subset of these regions can be expressed through these regions. All right, any subset of these regions can be expressed in terms of these regions. All right. So here we are, we have these. So these regions are expressed in this form. So if you consider the sets, this region 1 is A intersection B intersection C. Region 2 is A intersection B intersection C bar and so on. So this is how region 2, that is. This is region 2. Region 2 is A intersection B intersection C bar. So that is how we are, that is region 2. So these are the various regions which are shown over here. And if you, any selection, so if you take 1 and 2, so 1 and 2 is essentially A intersection B, and you can, express A intersection B, in terms of these regions. So you can represent 1 and 2 simply as the union of region 1 and region 2. So this is region 1 and this is region 2. So this is how you can represent. If you consider regions 1, 2, 3 and 5, so that is region 1, 2, 3 and 5. That is just A. So that this also can be expressed in this form. This can be expressed in this form. Alright. So this is how you can express various regions in terms of these sets. Alright. In terms of these sets. And so this is how you get the region A. All right. So what does A represent? So A, you can say, represents, represents that you have an item from this region, and A bar represents that you don't have an item from this region. All right. So you can see that A intersection B intersection C essentially shows that you have an item from each region. All right. You have an item from each region. And this region 8 indicates that you don't have an item from any of these regions. So on and so forth. All right. So you can say that an expression like this one. So this says that you have an item from region A but not from region B, or you have an item from region C. So these are expressions which can be interpreted with respect to this sense. Now you have what you have shown here is a Boolean lattice for two variables. So you have two variables, and corresponding to these two variables, we have constructed a Boolean lattice. So if you see, look at the structure. So you have got, so over here we had three sets. So here these two variables, you can think of these as two sets, A and B. So you can you can say that AB means that you have so two sets. You can think of these two sets as two basic properties. Uh, so this is an atom which indicates that your element has, it belongs to, let us say, set A and set B, or it has both properties A and B. It has property A, doesn't have property B, doesn't have property A, but it has property B. And here it says that you don't have either property A or property B. All right. So these are your atoms in your Boolean lattice. All right. And based on these, you are able to construct so if you consider the join, as you have seen just some time back, using the stone representation. So you're considering various subsets. You're considering various subsets. So if you consider uh, the join of AB and AB bar, you have this this element which this element in the lattice, which indicates that you are satisfying property A, and so on. So these are various. You can relate this to various Boolean expressions, uh, uh, and these Boolean expressions. So these various Boolean expressions uh, uh, you can think of these as elements in a Boolean lattice. So if you have two properties A and B, so these are all the possible functions that you can think that you can construct with two properties. That means you can have both properties, you can have one property but not the other, and so on. So, and what you can also see is that all of these are expressible as because these are the atoms. So you can express any element as the irredundant, irreducible sum of these atoms. That is what you studied some time back. All right. And these atoms uh, tell you these atoms. So atoms are, you can say, base combinations of these properties. So you have property A, property B, or you have property A, you don't have property B, and so on. So these are the base combinations of your properties. And using these atoms, you can construct all the other, or you can express all the other elements in this lattice. And as you can see, these elements essentially correspond to the various Boolean functions. So if you consider all the possible Boolean functions, those are present in this lattice. All right. So what you can see is that if you have two properties, you have, say, if you have, so you have 2 to the power 2 atoms. All right. You have got 2 to the power 2 atoms, and the total number of elements in this lattice is, again 2 to the power of that. So it is 2 to the power 2 to the power 2. So that is as many nodes or elements you have in this Boolean lattice. So those are all possible Boolean functions that you can have out of two variables. So this also shows how these functions are interrelated to each other in a Boolean lattice. Uh, so this also it clearly depicts the interrelation of these functions in a Boolean lattice. All right, and these base properties, these are called literals. When you write a Boolean algebraic expression, this is called a literal. So literal means, you know, uh, you satisfy a property A or you don't satisfy a property A. So that is called a literal. And so a Boolean expression is a string built from literals and the Boolean operators without violating their arity. And you can have grouping. So such an expression is a well-formed or syntactically correct formula. So you must have heard of the term well-formed formulae. Well-formed formula. So a well-formed formula is simply an expression which is uh, constructed using the rules of forming the expressions. And you have a fundamental product. Uh, a fundamental product is a literal or a product of two or more literals arising from distinct variables. So that's a fundamental product. And a fundamental product involving all the variables is a mean term. So these expressions which you see over here, these are, you might have heard of the term of a mean term. So these are the mean terms, and these mean terms are also, as you can see, these are the atoms in a Boolean lattice. These mean terms are the atoms in a Boolean lattice. And not surprisingly, all atoms, all elements in a Boolean lattice can be expressed as as an irredundant, irreducible sum of the mean terms. Okay. So this if you think about it, so if you have if you have k properties, you have already seen that if you have k properties, so if you have a1, a2, ak, if you have ak properties, then how many possible mean terms can you have? You can have 2 to the power k possible mean terms. All right. So if you construct that table, you are going to have so many rows, and each row will be either a 1 or a 0. Okay, it's either a 1 or a 0. So 1 simply means that you have, so if you call it m1, and this is m 2 to the power k. So 1 indicates that you have mi in your irreducible irredundant sum, and 0 indicates that you do not have mi in your irreducible irredundant sum. So how many possible sums can you have? You can have 2 to the power k possible sums. So this basically indicates that how many possible distinct Boolean functions you can have. Okay, how many possible distinct Boolean functions. So I mean, this is just another way. So they tie up, they tie up, and of course, you get this you get this from looking at the truth table. You also get it from the stone representation of a Boolean lattice, and as you can see, from the from the the irredundant, irreducible sum representation of any atom of a Boolean lattice, that essentially corresponds to particular one of these uh, uh, Boolean functions. So a certain choice of the mean terms. All right. So uh, okay. Um, Now we also have the concept of a fundamental product P1 is contained or included in P2 if P2 has all the literals of P1, then P2 implies P1. All right. So just to give you an example, so let us consider, this is a fundamental product, and this is also a fundamental product. All right. So let us call this P1, and okay, let us call this P1, and let us call this P2. So you see that P1 is uh, so P2 has all the literals of P1. Okay, so one second, sorry, is contained or included in P2 if P2 has all the literals of P1. No, I think I think I need to check this. There may be a mistake. Uh, yeah, actually it is the it is the other way around. I think there might be a mistake here. If I write this as P1 and this is P2, so in this case P2 implies P1. Okay, P2 implies P1. Uh, but I think there is uh, P2, in this case P2 is contained in P1, so P1 is contained or included in P2. Okay, if P2 has all the literals of P1, so yeah, so P2 has so this is all right. If P2 has all the literals of P1, I think it will be that is when P2 is contained in P1. I think it will be this way. P2 is contained in or included in P1 if, or rather, I would say that uh, one second. P1 is contained or P1 is contained or included in P2 if P2 has all the literals of P1. Yeah, that is all right. P2 has all the literals of P1. Yeah, okay. So sorry, this is correct. No problem with this. This is correct. So P1 is contained in P2. P1 is contained in P2, is included in P2. So the fundamental product P1 is contained or included in P2. If P2 has all the literals of P1, so P2 does have all the literals of P1, and in that case P2 implies P1. Yeah, that is all right. So P2 implies P1. That means uh, what you can say is that, I mean, see, when is so P2 implies P1. So whenever this property is satisfied, this property will also be satisfied. So that is quite evident because P1 says that property x1 is satisfied, and P2 says that not only property x1 is satisfied, in addition to that property x2 is also satisfied. So you can see that. So whenever this composite property is satisfied, that means whenever x1 properties x1 and x2 are satisfied, then of course property x1 will also be satisfied. So that is actually what this implication is, that whenever P2 is satisfied, P1 is satisfied. And here, as you can see, yeah, by the definition of a fundamental product, P1 is contained in P2 because P2 includes all the literals of P1. That is okay. Okay. Uh, so a sum of products, Now this is what you are probably already familiar with through the experiments that you have been doing. So a sum of products expression is a fundamental uh, is just a single fundamental product or a sum of two or more fundamental products. So so now this at this point you are able to relate to what you have been doing. I think you have been working with sum of product expressions um, in your lab. So this is how I mean you can relate this uh, Boolean lattices to the sum of product expressions that you have been dealing with. So these are all, as you can see, these are all SOP expressions. All of these are all of these are SOP expressions. These are all SOP expressions. All right. I mean, these are shorthands, of course. These are you have got some shorthands here. So this one is so this is just a shorthand. This is AB. So you have got some shorthands, and so this is just a compact representation of these expressions. So all of these are you can say, as you can see, these are fundamental. These are fundamental. These are sum of product expressions, SOP expressions. Yeah, and of course, all these properties you can use. All these properties can be used on these expressions because, as you have seen, I mean, when you apply these properties, you must know why those properties can be applied. So, so you have already learned the basis of applying these properties on the sum of product expressions. You have learned this from two angles. One is if you consider these as Boolean lattices, So you see that all of these operations are applicable on Boolean lattices, and if you consider these to be Boolean algebras, then those are uh, you know those are applicable through Boolean algebra as well. And you have also seen that this Boolean algebras and Boolean lattices are one and the same really. Okay, so functional completeness. So as you have seen, uh, if you wish to, so you might have a question that is, what are the Boolean operations that you need to express any Boolean function? So as you have seen that any element of the Boolean lattice can be expressed uh, as an irreducible irredundant sum. So for that you need this operation, that is a join, or if you look at it from a Boolean, if you look at it from an axiomatic point of view, you need uh, this plus operation, okay, uh, this plus or operation, and in order to represent these atoms, you also need complementation. That means a property is satisfied or it is not satisfied. So you can see that complement and along with or, these two are enough to represent any element in the Boolean lattice, any sum of product expression, or okay. So that gives you the notion of functional completeness. Now, uh, now once you have that, you okay. Once you have that, not an and. So you also need and to represent the atoms. So not an and, as you have seen. Sorry. Not an and. This not along with and. This is what you require to express any atom, and uh, uh, you can represent any element of the Boolean lattice as irredundant irreducible sum of the atoms. So what you can see is that not along with and or, these form a functionally complete set. Using these operations, you are able to represent any element in the Boolean lattice. Any element in the Boolean lattice. Now, now the interesting property is that if you define an operation such as NAND, then you can see that you can express these operations using these operations, and also De Morgan's laws. So what you find is that these are other functionally complete sets. So this is the basic functionally complete set. Not and an or. These together form a functionally complete set. But you can show that you can express. So for example, if you have NAND along with, of course, NAND along with 0, no, NAND along with 1, NAND along with 1, you can express all these operations. Similarly, NOR along with 0, you can express all of these operations. XOR and AND, you can express using XOR and AND, you can express all these operations. So these are various functionally complete sets of operations. And as you have seen in your earlier experiment, you can also use a multiplexer to represent any operation. You can also express a RAM. So this is interesting because how does the RAM help you to express? So let us just see how a RAM can help you to express. So let us just consider a truth table for X, Y, and Z. So you have got, these are the combinations of X and Y. All right, and then this one is 1 or 0, 1 or 0. So how does the RAM help you? So you can think of these as, if you have got 2 address bits, you can express these 4 possible addresses. So you can think of a RAM, which Sir, you are muted.
Sir, muted.
CRM, you are muted. And hello, I'm not muted. Maybe I think CRM has lost connection.
No. I've got
Okay.
muted. So.
Okay.
Okay. Yeah. So let me just. Yeah. So how we can express a function using a RAM. So this is, let us say, if you consider a function of 2 variables. So you have got this 4 combinations. So in the cell also, in the cells, I can just remember how the truth table. I'm basically remembering the truth table. Whatever I have here, I can just remember that, and that is how I can use the RAM as. So basically, this is my RAM. All right. So if I have 2 and this is my output Z, I can just remember the function. So that is how this RAM serves as a functionally complete module. All right. Okay. So I think I'll stop here. I'll stop here today. Okay. We'll continue tomorrow. Okay. Thank you. Then we'll stop here.